This is video 8 on our series of hypothesis testing, and we just covered how to estimate the variance of a population from a sample, including its confidence interval. Okay, we just covered this topic. The topic of this video is testing testing the variance inferred from a sampling of a population against a known population. And this is section 2.2.2 of Wessel's notes. So say previous studies inform you of the variance of a known population. Okay, so you know the variance of a population, and then say you take you make a sample from, say, a different location, and you measure its variance, and you ask the question, does the variance of the population sampled, so this is the variance of the population sampled, does that equal the variance of the previously studied population? Okay, so that's the question we're posing. And to answer that, we have to define our null hypothesis. Again, this is a hypothesis that is formulated to be rejected. And so the hypothesis is that the variance of the sampled population is equal to the variance of the known population. And of course, we have the alternative hypothesis that they're not equal. So let's look at an example, and our example is taken from Wessel, and we're comparing the temperature variance or standard deviation of temperature measured from a body of water. So let's say our known variance, or actually our known standard deviation, is 1.5 degrees C. So that's the known standard deviation. And we sample some other body of water. We measure the temperature 15 times. And we find that the standard deviation that we measure is 1.3 degrees C. So we want to know whether the variance of the temperature from where we've sampled is equal to the variance of the known population. And we're going to define alpha, our significance level in this example, as 5%. And our number of degrees of freedom is n minus 1, because we're dealing with variances, and that has n minus 1 degrees of freedom. In this case is 14. So that's what we're given. So I guess that's analogous to step A in the steps that we've taken before. Step B was to find the critical values of our standard variable, chi-squared. And so to do that, we need chi-squared of alpha divided by 2 is 0.025 for 14 degrees of freedom. And chi-squared of 1 minus alpha divided by 2 is 0.975 for 14 degrees of freedom. And let's turn to our table and look that up. So we have 14 degrees of freedom, shown here on this row. And we first want chi-squared of sub 0.025. So that gives a value of 26.119. 26.1, well, let's just round up to 0.2. And for our second value of chi-squared 0.975 for degree of freedom of 14, that's 5.629 or 5.63. So 97.5% of all possible values of chi-squared lie to the right of 5.63. Only 2.5% of all possible values of chi-squared lie to the right of 26.12. So those are our critical values. Step C was to calculate chi-squared from our sample, and that's, again, n minus 1 times s squared over the variance of the test the population that we're testing against, and that gives 14 times 1.3 degrees squared all over 1.5 degrees squared, and that gives 10.5. Therefore, our result is that our calculated value of chi-squared lies within the range defining our confidence interval. It lies within the most probable range. So there's no reason to reject the null hypothesis. The null hypothesis being, again, that the sampled variance is equal to the known population variance. So H0 cannot be rejected. And we're left to reserve judgment. Now let's consider a slightly different test. Suppose we want to know whether the variance of the sampled population is less than the variance of the known population. And we might be motivated, for example, by the fact that we see the variance of our sample is less than the variance of the known population. So we want to know whether we pose this question. And so to answer that question, we will define our null hypothesis as the variance of our sampled population is greater than or equal to the variance of our known population. And if we pose that null hypothesis and reject it, then we can therefore show the alternative, that sigma s squared, the variance of our sampled population, is indeed less than that of our known population. So we've already done step A. We've already made our sample and we've measured the variance. And we know that n minus 1 equals 14. And so the next step is to define the critical chi-squared. And this is based on, let's say alpha is, let's keep alpha at 5%, the 5% significance level. So now let's think about this. If indeed this population, the variance of the sampled population is greater than that of the known population, then our chi-squared statistic, which again is n minus 1 s squared over sigma squared. If we sample a population with a greater variance than the known population, then chi-squared should tend to be on the higher side. So let me draw out this probability distribution, and I'll sketch out a chi-squared distribution, and we're going to define our critical values of chi-squared. So this possibility, the null hypothesis, is testing, well, if the null hypothesis is true, then chi-squared will tend to be in this range, right? This will be the range where the population, the variance of the sampled population is greater than that of the known population. And this region will be relevant for the possibility that the variance of the sampled population is equal to the known population. So our test is really going to involve seeing if chi-squared falls within this range. And this is going to be our alpha. The area under this part of the curve is going to be alpha, and that's equal to 5%. Okay, we don't care about this area. We're just testing to see if it's in this area. And so this corresponds to chi-squared of 1 minus alpha, so that's 95%, and again, 14 degrees of freedom. So to find that critical chi-squared value, we go to our trusty chi-squared distribution table, and we look under our degrees of freedom is 14, and we look for chi-squared 0.95, and that's 6.57. So our critical chi-squared value is 6.57. Is that what I said? Let me double check. 6.57, right. Okay, so we already know that our chi-squared value was equal to 10.5. And if we're going to reject the null hypothesis, then chi-squared has to be less than this. And so chi-squared is not less than that. It's greater than chi-squared, our critical value. So again, we cannot reject H0. There's no reason to suspect that this is not true, that the variance of the sampled population, there's no reason to suspect that the variance of the sampled population is not greater than that of the known population. Okay, and again, we're left to reserve judgment. So the test of our null hypothesis involving a greater than or equal to sign, therefore, was a one-tailed test. It was a one-tailed hypothesis test because we were interested in knowing whether the chi-squared value fell within one tail of our chi-squared distribution. Okay, so that wraps up our coverage of the one sample test of variance against the variance of a known population. That's our one sample variance test.